Hello, everyone. We're here to talk about quantum. Thanks for joining us. It's a great afternoon, beautiful weather, and we're looking forward to talking about some cutting-edge technology. I'm glad you're here to join us. My name's Wade Davis. I'm the Vice President of Computational Science and the Head of Digital Research at Moderna. And I want to make you more aware of quantum and why we're excited about it, and also connected some other things. We've seen a lot of sessions on AI, so I'll draw those two things together, and hopefully you'll come away as excited as I am and learn something new about the possibilities that quantum offers. I'm joined here by Heather Higgins from IBM, and I'll let her tell more about herself.
Yeah, Heather Higgins from IBM. I am part of IBM Quantum. Specifically, I lead the industry and technical services team within IBM Quantum, and our mission is to work with enterprises who are doing applications research and applied research so that we can come up with some fun things to do that make a difference in the world.
So just to help us take a temperature of the audience, yesterday in a quantum session they did by a show of hands, how many feel pretty comfortable with concepts of quantum computing? All right, so I'm guessing that looks 20 to 30%-ish, Heather, so maybe we'll use that to kind of calibrate which direction we go.
And we're going to really focus on the applications more so than the technology. Although the technology is really powerful, I'll just say a few words to ground everyone, and then we'll show a little video. Quantum computing is very different than the classical compute that we use today. It is based on the principles of quantum mechanics, not intended to replace existing classical compute, supercomputers. It is meant to be complementary, right? So that's really important to understand. And the one thing that it does a lot of really cool, fun, weird things, but the one thing that it does that's really, really powerful, especially as we're thinking about enterprise applications, is it is probabilistic, and it enables you to look at a diverse sequence of data and instances simultaneously, not sequentially. So we're going to do try a little exercise right now. Imagine if you were walking into this room, and as you walked in, you were given a gift box. And everyone in this room had a gift box, but you weren't allowed to open it. It has South by Southwest swag. And there's one or two that might have something special. And so in order to find out who had the something special, we would ask everyone to open up your gift box one at a time. So the person who's sitting over there, and then the next person, and then the next person. It would take us quite a bit of time, right, to go through everyone's opening up of the box. In quantum computing world, you can do it all at the same time. So we'd say 1, 2, 3, go. Everyone opens up their boxes. So that's just an example, a very, very simplistic example of some of the power of quantum computing when you are working with probabilistic and the opportunity to parallelize a lot of things. We're gonna do a little video just to make quantum computing applications tangible.
Quantum computers are meant to address problems that cannot be addressed by classical computers. Things like finding the right materials to enable carbon capture, to really bring the fight to climate change, to address more efficient fertilizers that can not harm the earth, but also continue the food supply chain that we need to feed the world. Also, there's some fundamental questions of how our universe is stitched together and how matter behaves at the atomic and subatomic levels that we need to know. It's the next frontier. Let's take one area of research already underway, the search for new batteries. Batteries have transformed our lives by allowing us to carry computers and smartphones, but there's more to be done. Batteries are crucial to our clean energy future. Whether it's powering electric cars or really pushing renewable energy, we need a fundamentally different chemistry to create the batteries for tomorrow. Quantum computing would allow us to effectively look inside the battery during its very complex reactions to enable us to think about new materials and the structure of the batteries that are going to be needed to power the next generation of devices. How do we get there? By building the world's most advanced quantum devices in a developmental platform and making it available to the world. Only by working together now will we be able to solve the problems that we'll be facing together in the future.
So hopefully that grounds you in the promise of quantum computing and why so many of us are enthusiastic and excited. I want to actually start to ask Wade a few questions. As a business leader who is evaluating the promise of quantum technology for Moderna, can you talk a little bit about what got you excited, specifically about quantum computing, but then also about the applications for the biotechnology industry?
Yeah, so just starting off kind of from a broader biotech view, a few things kind of about Moderna that kind of sets the table of why we would take a direction like this that might be perhaps surprising compared to other pharmaceutical or biotech companies. As I think the world came to see during the pandemic, Moderna does things differently, and we do things that people said weren't possible, right? If we looked at traditional approaches to vaccines, at that time, no one had ever done anything that fast. The technology had been around, but we were still trying to convince the world this was going to work. So we like to do things differently, some things that others might not believe are possible. We also believe in taking some risks, and that's encoded in our Moderna mindsets. We accept risk, and a new technology is an example of that, like quantum. It's still growing and learning and developing, but that's where things are exciting, and that's how you stay ahead of the curve, right? Once something's already there, the risk is out, right? You're not taking a risk, you're playing it safe. So if you're going to stay on the cutting edge, you're going to have to take risks. And so in terms of biotech and looking at that, that is what that opens up, a new frontier, new possibilities. And we accept that risk, and quantum's a perfect example of that. It's a convergence of technologies. And an example or analogies I like to make, if you think of examples when different technologies come together, you might hear the term convergence of various possibilities of technologies, and together that exponential combination of what's possible. So quantum really reminds me of where we're at in the quantum technology realm right now. If you think about other examples, one of my favorites are digital photography and cameras, and how you put that together with phones. When that got miniaturized and put on your phone, everybody now carries around a camera, right? We don't see anyone with a camera anymore snapping pictures. I'm sure they're out there, or the professionals maybe. But if you think about that enabled so many new technologies and just changed our world, right? And so the convergence of those technologies, we believe that type of convergence with quantum computing and biotech can really open up a lot of possibilities. And I'll talk more about that. But really, an example of something you may not think about, how that example of cameras and everything changing, your genetic sequencing, that everybody's holding in their hand a little camera on their phone, that was actually enabled through these cameras. The technology that allows us to make a lot of breakthroughs in biotech came from a source you wouldn't think of. So when things come together like that, it opens up new possibilities. So we think quantum combining with these other technologies will really open the door for great possibilities.
So we should expect the unexpected.
This is true.
So we've been working together, Wade, for just under a year.
That's right.
Moving fast, as everything in the technology world does. There's so many exponential number of use cases, and there's so many different problems, right, that face us in business society today. So can you share a little bit about how you get started and where Moderna chose to get started with quantum, just to give folks some perspective, right? You got to kind of, I always tell our enterprise clients that you got to dive in, right? There's no wrong place to start, but you really need to start. So talk a little bit about how and where Moderna has started.
Sure. Well, when you think about biotech, I'll jump into the specific example. You can think of, you think proteins, mRNA, chemistry, if you think pharma and biotech. So to set the table, as you can imagine, mRNA is where I'm going to go here. But to set the table for some of this technology, let's play a quick clip here.
The most powerful defense against disease has always lived within each of us, our immune system. And now, after a decade of research, Moderna is introducing mRNA-based technology that can unleash the immune system's ability to help fight disease like never before. Here's how. The human body uses mRNA, code-carrying molecules made naturally in our cells, to provide the instructions for life. By harnessing mRNA, we can teach cells to make the proteins we need to help fight disease. The trick is getting the instructions into the cells, because as incredible as these messengers are, they're also incredibly delicate. The breakthrough we needed was the development of lipid nanoparticles, or LNPs for short. LNPs are tiny fatty droplets that carry mRNA safely, like a shipping container. They're called nano for a reason. They're just 100 nanometers across, 1/100,000th of a centimeter, and surround mRNA, forming a protective shell for their journey to our cells. As soon as the LNPs accomplish their mission, they dutifully dissolve and disappear, helping our immune system defend us. Our mRNA technology has the potential to change the way we help prevent and treat viral diseases, cancer, and rare diseases in ways previously unimaginable. It's innovative. It's here, and it's ready to help change medicine as we know it.
Great. So I think this sets the table to help you understand what is needed in order to come up with breakthroughs like this. So when you develop a therapeutic or a vaccine, you need to target a protein. These proteins can be variable in length. I'll give you an example in a few minutes of what it was like for the COVID spike protein. But basically, you have a long sequence of words, if you will, amino acids that are put together to form a protein. There's a lot of ways to encode those. If you go back to your biochemistry, you encode them in a mRNA sequence, which then gets translated into a protein. There's not a one-to-one map of the letters that you use to build each one of those building blocks. So two analogies to kind of maybe not belabor it, but just depending on everybody's refresher here on biochemistry, I'll make some non-kind of science analogies. Imagine you took a long string of words, here a sentence or a paragraph, but let's just start really simply with a sentence, like the black cat crossed the street. Imagine that's our protein, that's what we're targeting. You could say an equivalent statement like that, like the black feline crossed the street, or the black cat crossed the road, or a cat crossed the street, or a dark feline crossed the road. Do you see how many possibilities, how many ways I could encode to get the same meaning of that sentence, right? So when you think about you need to target a fixed protein sequence, there's lots of mRNA sequences that can get you the same final result. Another way to think of it from a physical, imagine you had to build a block of Legos, and hopefully everybody's had the pleasure, my kids love them. You know, there's a lot of equivalent ways to get the same. If you had to make a cube of 20 by 20 by 20, right? You could pick a 2 by 1 and a 4 by 4. You could come up with plates. You could make that so many different combinations to get there. So what happens if you take like just the spike protein that was used to make the COVID vaccine, and you start doing all the multiplications of, well, I could right in this spot, I could pick A or B, and I could do C or D, or I do all these possibilities. You start multiplying that through. It's a really, really, really big number. So it's 10 followed by 623 zeros. So to just remind everybody, a billion is 10 to the 9th, and a trillion is 10 to the 12th. Google, the namesake for the search engine, is 100 zeros. The number of estimated, I should say, nobody knows for sure, particles in the universe is 10 to the 80. So when you think about, if you want to calculate all the possible ways just to encode a single protein, and this one's a relatively small one, it gets crazy. And just one last way to think about how many possibilities there are, imagine every particle in the universe at 10 to the 80. And inside that particle, pick a random particle, inside of that was another universe of similar size, another 10 to the 80. And inside of one of those, now you're 2 layers deep, pick another random particle and grab another 10 to the 80. You would have to do that 7 times, okay? You'd have to have 7 nested universes inside of each other, and you still wouldn't get to the number of possibilities that just to encode the one target protein. So this is a hard problem. I hope you're convinced. It is a hard problem to figure out. And so that is the types of problems that we're attacking classical means, but we're really excited about for quantum computing, because as you can imagine, the example that Heather used about opening the packages, we would like to explore all those possibilities, but there's not enough known classical compute power to ever, that's basically infinite space and would take infinite time to search. So, it's about doing that. It's also not always about being faster. It's also, compared to other methods, getting into, that's a very big space. We can think of it as a hyperspace, kind of a theoretical concept on lots of dimensions. You'd like to be able to explore different parts of that space. So even if you got an answer that was just as good, allows you to get a diverse number of solutions to actually try out. And 2 other applications are protein engineering, and I'll bring tie that example back to the COVID. And since the home crowd here at UT Austin, you may be aware that the spike protein was a modified version by researchers at UT Austin. So they had to do some protein engineering and protein folding. We didn't just target the native version of that protein. So computationally, you'd like to model other things in mRNA, and the protein structure is a very also complicated structure because there's all kinds of conformations that proteins can take. So that's another application that we're excited about. And then that kind of goes hand in hand with molecular simulations and just understanding nature at a subatomic particle level with quantum chemistry. So mostly mRNA, that's what we're focused on, but then there's other possibilities that follow thereafter.
Great, those are fabulous examples. We're going to put a slide up just to show everyone some additional examples by industry. I was in a panel yesterday, and questions that we get a lot are a few. One is which industries are really diving into quantum, and which industries aren't. And if you asked me the question, 5 years ago, I might have had a different answer. But the reality is today is that we're seeing traction from all different industries. I would be really hard pressed to be able to identify one industry that is not already starting to look at quantum. The way that they approach the types of use cases may be different, but they're all really taking a look at quantum as a serious additional complementary compute that they can add to their arsenal. So if you look, you can see, by industry. I can't read the slide from here, but that's okay. You'll see things like anomaly detection. That's a really popular one. Anomaly detection in discrete manufacturing. It's also used in financial services for fraud detection. Payment, lots of different types of fraud. So those are some of the examples. When we peel beneath that, because again, endless possibilities. You saw some examples in the videos that we shared. The types of use cases that we're focused on haven't changed over the last, 10, 7, 5 years. The video that we showed you was actually a video that we were using 4 years ago. The only thing that changed was that Katie, who was presenting, was promoted in that time. So there's, as much as the technology is changing, as much as there's research and there's advancements in the industry, it can be mind-boggling to get your arms around it, your brain around it. The use cases that we're really looking at haven't changed. Within IBM, and I think it's becoming convergent in the market, we really look at 3 broad categories for quantum computing. We look at the ability to simulate nature. That's where some of the physics and the chemistry use cases would be. We also look at advanced mathematics and complex data structures. That's where a lot of your AI, machine learning type use cases would be. And then also search and optimization. So 3 very, very broad categories. And then within those broad categories, we look at about a dozen problem types. So you can imagine within simulating nature, we're looking at problems around vibrational or electronic structures or lattice models. Very, very focused there on material material discovery, creation, design, across many, many industries, not only life sciences and biotech, but within aerospace and defense, within automotive, within a lot of consumer goods industries, right, around how do you build sustainable material. We also look at within advanced math and complex data structures. That's where a lot of your classification and clustering problems would be, right? Very, very traditional areas of focus for AI and for machine learning. The other thing that we look at would be within optimization, and so within optimization, right, your combinatorial optimization, your traditional traveling salesman, the vehicle routing types problems. So those are just some examples of while it becomes endless, we look at the categories, we look at the type of problems within those categories, and then we look to identify problems so that we can get really focused on what type of algorithms, what types of encoding approaches, what type of data we need in order to bring out the advantages that quantum promises. I think one of the things, Wade, that we might want to talk to, and we can take the industry slides off, you spend a lot of time also, not only in quantum computing, but with AI, right? And so I know you've got very strong points of view around how to think about AI and quantum, are they competitive? Are they complementary? What's your perspective?
Yeah, thanks for asking that. It's one of my favorite questions. So they're definitely not. They can be in some places seen as competitive, but that's a very narrow overlap. They're different. They're complementary. Quantum computing is a way to compute something in a non-binary fashion, using probabilistic bits, if you will, qubits. So they're just really apples and oranges, are even different fruit, I would argue. They're not competitors. So they can definitely solve similar problems, just like if you're familiar with graphical processing units, GPUs, right? NVIDIA, everybody heard so much about them in the stock market lately. So they're the number one maker of GPUs, and GPUs have been around initially for video games, right? That's where everybody had, that's what they were used for 20 years ago. And then their physics engines and other things became possible, and realized it was generalizable to things like tensors and other uses. But that's an example of, a technology, a GPU, that is used to complement the traditional classical CPU. And if we think of, QPUs, quantum processing units, as some people might call them, I think it's going to go in a similar direction. Another speaker yesterday, at the same time of the day yesterday, said it was kind of like comparing an airplane to a rocket. It's not like you're just going to transport everything with rockets. If quantum's a rocket and classical is the airplanes, they do different jobs. You wouldn't transport everything around, right? With rockets, it's just that's overkill. So similarly with quantum, AI is being used to make quantum better, right? For the error correction and even the manufacturing and lots of places, right? AI is everywhere, and it's being used to make quantum better and the circuitry and all that. But still, the technologies are different, and I think we'll be using it for specialized problems when needed. And there's definitely problems in classes that we can talk about where they has distinct advantages in cryptography and other things. But definitely they're not competitors. They're going to be working hand in hand. But on the other hand, I like to tell my management, we're not going to be doing emails or even on your under the desktop quantum computer. That's not where the technology is going to go. At least for the foreseeable future, it'll be partnered like in the cloud, and you access it at very specialized centers with hardware. But that's exactly how classical computing started, with large mainframes, right, that were very specialized to use. So definitely not competitors, they're complementary.
I won't be putting a quantum computer in my pocket anytime soon, right?
I don't think so.
So, riffing off of AI, so where there's AI, there's data. There's lots and lots and lots of data. How do you go about thinking about the daunting amount of data on AI? Then when you talk about quantum, they are different, and all of the data that a biotech firm as Moderna would be dealing with, especially as you start thinking of personalized medicine, individual medicine, DNA structures. How do you think about data?
Yeah, this term's been around for a while now. Data is the new oil, or I think that's maybe a term that everybody's very familiar with now, so it's maybe a little passé. But yes, data is key to so much, especially in a research-driven company like ours, and lots of companies have recognized that's so important. So we want to stay on the cutting edge to help patients and be competitive and do the best we can do. So that really comes down to, how can you acquire data in order to get that in a cheaper way, and what that enables. A story I like to, maybe you've connected these dots before, but if you haven't, that really the breakthroughs that we're seeing today in machine learning and AI, if you think of Siri or Alexa or ChatGPT, any of the large language models and the precursors to that, they really come down a lot to these, again, that are in your hand. And that's because a lot of the breakthroughs with their precursors in neural nets, the math was there, but the data to train and learn wasn't there. So if you just pull on that thread and you trace back how the availability of data was so essential to those breakthroughs, it really comes down to, I need to be able to collect data really cheaply and easily. And those cameras I alluded to earlier, well, we're all carrying one. And then Google says, would you like to store your pictures? We'll store them for free for you. And that enabled them to have lots of data to train their models just to image recognize things for free. And in some cases, you paid them to hold your data, which then they used. And every time you interact with Siri and Alexa, there's a disclaimer. If you've not noticed, usually it's right when you install. Can we use this? Well, they're using that feedback from all the voice and the conversation. That's a little harder in biotech because the data acquisition is not so cheap, right? Sequencing someone's DNA, just, no, people aren't, that would, if the ability to access tumor DNA, right? Every time everyone had had cancer or a malignancy and you had access to that, or your germline DNA, ignoring the privacy issues, but I'm just making a point about data. If you had that as freely available, the medical breakthroughs that would be enabled would just be tremendous. And so being able to lower those barriers of acquisition really helps accelerate things and would help accelerate the machine learning and the quantum across the board. So, I think we're getting there. The cost of genetic sequencing, everything's going down. Technologies are converging, but we're not there yet. But that's the type of things that we need as a research company, is to get more of that data and drive the cost down to acquire it.
Yeah, I'd say it's a challenge across all industries, and one of the things that I share when I'm working with enterprises in all industries is the challenges, right? So often the focus when we're getting enterprises on board with understanding quantum computing and taking the first steps of their journey, which is often around educating and is building capabilities. We get really focused on the programming. We get really focused on the change. And data kind of gets left to the side, but it's so critical. Just like in AI with classical compute, the type of data that you might be looking at might be different than what you would normally look at for AI. The way that you transform the data, the way that you encode the data to be able to work within a quantum computing context is very different. And so it's a big learning curve and it's a challenge. I think we've learned a lot from getting data ready for AI. So we've got a little bit of a foundation, but now it's around, okay, Now, if we want to start looking at AI and quantum in a symbiotic fashion, where quantum is complementary AI, what are the different things that we need to think about as we're gathering data, as we're storing the data? So again, yeah, big challenges, lots of opportunities.
Yeah, so Heather, as we think about the utility and the time to be exploring it, why now for quantum?
Well, I am really excited. There's been decades and decades of research and enthusiasm for quantum, a lot of scientific advancement. We see, an industry that's being stood up around it. We have a very vibrant and robust ecosystem that includes academia, that includes government, that includes enterprises and industry, that includes startups and channels. And there's just a lot of innovation that's happening with this ecosystem that's sharing and collaborating and working together to move the field forward. So a robust ecosystem. There is government funding from many countries that is being poured into the technology, both to be able to advance the technology and also for economic development. So there are national strategies that are really being stood up. So you're seeing all of these things where the industry is getting put into place, and people are starting to think about the value creation chains outside. Why I'm really excited as someone that works with enterprises to bring useful quantum computing to the market and to enable quantum to be used for something useful that you couldn't do previously are some breakthroughs that we made. So over the summer of last year, so about June, July of 2023, working with University of California, Berkeley, we were able to publish some really exciting results around error mitigation. Where the first time we were able to get useful results out of the quantum computing at a scale that is meaningful. What I want to do is just put a video, we're going to show a video, and bring you inside what that looked like for the team, and then I'll come back and I'll talk about it, okay?
So honestly, I was pretty nervous. We were running a really challenging experiment to explore the limits of today's quantum computers and how they compare to classical computing methods.
I try not to view this as a competition between classical and quantum computing, but I did go into this experiment expecting the supercomputer to outperform the quantum computer. So my involvement in the project was to help simulate this quantum experiment on some of the largest and most powerful supercomputers in the United States, including at the Lawrence Berkeley National Lab and the National Energy Research Scientific Computing Center.
We wanted our collaborators at UC Berkeley to use classical simulation methods to verify whether our noisy quantum processor was producing reliable results. We also wanted to push our device to limits where their methods might struggle. We didn't want them to come back to us too soon and say, yeah, we solved the problem very easily.
But using some of the novel error mitigation techniques that IBM has introduced, we actually found that the quantum device easily matched exact classical results and outperformed approximate classical results in cases where the exact answer was available. Impressively, even as we moved to circuits beyond exact classical methods, quantum still appeared to be more reliable than some of the approximate methods that we tried on these large supercomputers.
For quantum hardware, scale and noise have always been the biggest problem.
On scale, IBM's made more progress than anyone else, but noise is a different problem altogether. Quantum computers are very sensitive to noise, disturbances that cause errors in their computations. IBM has spent years developing methods for filtering the effects of noise out of quantum computations. This is called error mitigation. We were only able to do this because we've now built a quantum system of unprecedented scale and quality, and developed the ability to manipulate noise on a quantum system at this scale.
Having good, reliable 127 qubit devices with high coherence times was really a prerequisite. The hardware really enabled this project to happen.
We wanted to see if error mitigation would allow the quantum computer to even keep up with the accuracy of a classical supercomputer at this scale. With the error mitigation techniques used in this paper, we run our calculations and slowly turn up the noise. Then we extrapolate back to the zero noise solution.
How do we control and manipulate hardware at this scale is quite unprecedented. The answer to this question did not exist before.
Understanding the root cause of these discrepancies will allow us to improve both methods and is an example of the benefit of the interplay between quantum and classical. Together, we can realize a device that can solve interesting problems.
As we increase our number of qubits, reduce our error rates, and improve on these techniques, we will see a growing collection of problems where quantum computers can provide value.
Eventually, we'll reach a point where we can truly learn something new from quantum computation that we weren't able to access through classical alone. A point where we can really push at the boundaries of human knowledge.
So the key point there, and one of the reasons that I'm so excited, is that we were really able to get, noise has been a challenge, right? But with this error mitigation, we're really able to get to solving a useful problem with useful results on a very complex problem with scale. And the scale beyond what at the time, could be done with classical compute. So one of the things, we talked a little bit about AI and quantum, we talked about classical compute and quantum compute. They're a very symbiotic relationship. There's, leapfrogging, and the technologies push each other, which is really exciting. We brought that paper, published the paper, it was on the cover of Nature in the summer of last year. Since then, we've made some additional advancements. We released a error correction code toward the end of the year, which shows a lot of promise, a lot of work to do, but an error correction code that has enabled us to bring error correction forward in our roadmap. We're looking at 2029 now for being able to introduce error correction. And what that means is the ability to really do useful quantum computing and to be able to work with industries to do things that are beyond what they can do today with a fair degree of confidence. Now, it's not today. But we actually can start to build those utility scale prototypes. And when you're building those utility scale prototypes, it enables you to start thinking about what those prototypes would look like in a pre-production environment. And there's an enormous amount of learning that happens when we start looking at how would quantum actually be integrated into an enterprise. What are the data decisions, the data strategy, the encoding and technical strategies, how is it working and integrating with other technologies that you have? And so the reason I'm really excited is because we actually can do something tangible, and we're moving from just doing discovery and just doing research, which will continue to be important, to also being able to look at the applications of quantum and to be able to really understand the power and the impact. And I don't think it'll be a moment in time. I think everyone asked that question. Quantum advantage, which use case are you going to get to, which application is it going to be, in what industry? It's going to be, in my view, a series of moments, where initially you're looking at very tailored applications, tailored data with very specific, targeted pilots in an enterprise, and we're going to learn. And then we're going to have another moment and another moment. And so I think as the technology starts to mature, and we start to be able to really test it in real world, we're going to see even more of a catalyst for innovation. So that's one of the reasons that I'm excited. I know that there are lots of intractable problems that are out there. The more you know, it seems like the more we realize that we don't know. And so I think just the promise and the utility and the entire ecosystem working together to support each other to do something that we haven't been able to do before is within grasp. We've updated our roadmap in December. And so our roadmap now, as we're moving into the era of utility, goes out to 2033. We also have introduced error correction earlier than we thought for the advancements. And you can start, as you look at it, I don't have it here to show, but it is public. We can look at the processors, the qubits and the gates that we can use, and you can kind of see year by year the robustness that we're bringing. You can also see that we're looking at different personas. We're looking at what a quantum physicist is going to do lower in the stack, a research scientist, and the tools that they're going to have available to have quantum computing be a useful discovery tool. And then we're also looking at data scientists, or a combination of data scientists and computational scientists within an enterprise, and tools to abstract the complexities from quantum to make it more consumable within the organization. So yeah, I'm excited.
Awesome. That was a nice example of collaboration there, as you showed with this paper. Tell me how IBM is using their partnerships and collaboration and network to drive innovation at scale.
So with Big Promise, means no one organization can do it alone. I think we're very aware of that. Partnerships are so vital, they're so critical. Within IBM, we have IBM Quantum Network. We're at over 300 members now. And again, just like I said earlier, when talking about the ecosystem, that membership includes government, academia, research institutes, industry enterprises. It includes startups. It includes channel partners. So it includes a lot of various perspectives who all have a different view. So that's the importance of partnership. I think as we work with the enterprises like Moderna, really, really important. We each have our different domain expertise, and putting together the expertise that Moderna has around mRNA, together with the quantum computing expertise and our industry expertise. It's really the synergy of different expertise coming together that's going to enable us to go faster. So we have Accelerator, which is what we use to help organizations like Moderna build their internal capabilities. It also is how we start to build prototypes, but we learn together. And one of the things that is most exciting to me is watching organizations like Moderna building the capabilities and coming back and questioning, why is it that we can't do this, or could you ever think about doing this? And so we take all of that information and it really influences our product roadmap along with all of the other inputs from the industry. Yeah.
Yeah, and we've got some work. Hopefully we'll update people in a few months about some of our findings there. It's very exciting. As we look to the future, what do you see? What does it look like to you? I know you've kind of alluded to some of that with the roadmaps, and I'm happy to weigh in as well. But just what do you see as the future of quantum?
I think that we're going to see the arrival of quantum computing before, as an industry, we're ready. I think quantum is very different, and just like we've seen with other emerging technologies, you talked about, right? AI technology was there perhaps before the data was there to really fully exploit it. So I do think that the technology is coming in. We've done a lot of science discovery. We're now really focused on the engineering aspects, and within the community, we know how to solve some of the engineering aspects. It's just a matter of time. Our roadmap reflects that. But in order to really have quantum adopted, it's really about the workforce, right? And it's having enough folks who understand enough about quantum computing. Not everyone's going to have to be a physicist. We'd never get anything, out to the market. Technology companies are working to abstract the complexities to make quantum computing more consumable within the industry, within the marketplace. So I think that the things that get me really excited, if you just remember going back to some of the videos, the things that we will be able to do. Think about how they will become personal for each of us, right? Drug discovery, therapeutic, medicine. Can we reduce the carbon footprint? There's so many things that are out of the realm of what's possible today that are now really sneaking in. So I think as we start looking at enterprises being able to address some of the supply chain issues that arose during COVID, there's so many different possibilities, and we're really within reach, and we have such a broad and diverse ecosystem. And I think partners Wade, like Moderna, who's taken the risk and coming on the journey. And pushing us and challenging us, and really, looking at how are you using the diverse compute capabilities that will be at your disposal to solve the problems that your organization is trying to solve.
Yeah, just to riff off of some things you said there. There's a balance between what the capabilities are and then the algorithms take advantage of them. the underlying math for the convolutional neural nets, it was a precursor to the large language models and AI. The math was all there in the 70s and 80s. There's just no computers that could do anything meaningful to compute anything with them. And there wasn't data. So you really need the three things, right? You've got to have something, a good problem. You've got to have the theory and the math there, the algorithm, so to speak, that's been developed. And then you have to have the computer that's capable of running it. And so if those things kind of get out of stoichiometry or balance, then you're kind of not hitting the full potential. So I see the need. Maybe if we take, we've got a few minutes here. We're doing good on time. If we think about what's so different about quantum computing, you can't take general classical algorithms and just try to port them to quantum. You really have to take a very different approach to thinking about what it is you're dealing with. And so a lot of efforts out there in the community, I think, around algorithm development would be key. And it's really just getting, more education and exposure to that, so that as the hardware grows exponentially, as IBM and others hit their roadmaps and put that out there, that we have a good workforce that's ready, and then the theorists and the algorithms have been developed to run that. People probably don't know, but you can get on. I mean, it's not much work to get and run something on a small quantum computer right now for free. My high schooler was running stuff, before he even entered high school on a quantum computer. So it's IBM's done a fantastic job of putting some open source software and some older generation quantum computers out there for people to start understanding in their head around that. Because it does take some time to kind of get up to speed about that, and that plays into getting our workforce ready and getting students and the next generation ready. But I applaud IBM for really taking a lead and putting open source. A lot of great training material. They have a code of summer out there I think it's usually limited to about 5,000, I think, folks around the world, where they get out and try to educate people to get their hands dirty and kind of like a collab, Jupyter Notebook style, interacting with a quantum computer. And so for those who want to get their hands dirty or if you're familiar with computing but not so familiar with quantum, you can get in there and see what it's about. It is very different. You're thinking in terms of circuits, unless you did computer science, maybe in logic gate thinking back in the 60s and 70s. You probably are now, it's been abstracted away. You're used to dealing in a higher level language. So when you go to quantum and you start thinking, it looks like you're dealing with wiring diagrams. It's really a very different animal. So I think it's great material that IBM's put out there for that.
Yeah, we've put a lot of material out there. The ecosystem has put material out there, and I would, just for those of you, has anyone here, I know that when we put the hands up at the beginning, there was like 30% of folks that, were somewhat familiar with quantum. Anyone who has tried to engage in the industry, like hands up. So we don't all have to be experts, but there's obviously curiosity that's here. Great, so my recommendation is just jump right in. It can be daunting, and there's a lot of work to abstract the complexities, to make it more consumable, but right now, lots of tools out there. I would read. There's a lot of research publications that are out there. It's crazy. You think AI is crazy. It feels like there's a new innovation every day. There is so much really good work, in the science community for quantum. LinkedIn is a really good, if you're, you can just go in and search on quantum. And there are so many quantum experts that are out there sharing their work, that are willing to engage, and that will, as they're promoting their papers out there, really focusing on why it matters, right? And that why it matters is really important, to start to put all the different pieces together. There's no dumb question. I think, we've worked and trained, classically trained data scientists, as well as, quantum, physicists, folks that have a quantum, STEM background. The learning curves are different. A lot of times the hardest part for the classically trained data scientists is to unlearn everything that they think about how they're going to approach a problem. So there's just, there's different learning curves, but it's an exciting field. The promise you saw my enthusiasm, Wade's enthusiasm, you saw some of the videos. The promise is just really, really exciting. There's a lot of practical applications within multiple industries that will help them, do the things that they can't do today. And so I would just encourage you guys to be part of the movement, be part of the excitement, be part of the enthusiasts. The questions are what's going to drive us all, faster, and into areas that we can't even imagine today.
Awesome. Yeah, I'm super excited about this. We're hoping to see breakthroughs in the science and the possibilities, obviously, with mRNA design, but as I mentioned earlier, protein folding is ripe for understanding. Our world is a quantum mechanical world, and so when we try to simplify things in a deterministic world, we're not going to really be able to emulate that complexity. But quantum computers, right, takes us back to reflect that reality. So when we're doing simulations and quantum chemistry, it's going to be, fantastic stuff that I'm sure some people will be talking about in a few years, some of the breakthroughs here at South by. So it's so excited to talk about it and to see what we can do to impact patients and have better lives through, of course, biotech and pharma, but other application areas, as you've mentioned. Well, thank you, Heather, for joining me up here. We finished a little early. We'll hang around. We won't be taking questions, but happy to stick around and talk to anybody who wants to follow up with either of us. Thank you all for joining us.
Thank you.